Alright, so this is the cardiac cycle diagram. It's also known as the Wiggers diagram because it was created by Dr. Carl J. Wiggers, who, as you can see, graduated from the University of Michigan in 1906. So this diagram has been around for over 100 years. And when I looked at this diagram the first time in school about 4 years ago, I thought, what the heck is this? And I'm definitely going to fail my exam. But I broke it down after a while, and I'm going to try to do the same. And it wasn't that bad after breaking it down. So let's get started. Why are we even studying this? Like, why are we looking at it? Well, we're measuring the function of the heart, just like you measure the function of like anything else. Like if you're measuring heart rate, you can be measuring like how many beats per minute. You can measure respirations. There's a respiratory cycle too. There's a diagram. Even stepping away from the body. Think about cars. You can check the fuel level, the gas level, all those things. What if something's wrong with one of those? Well, you might have to take the car to a body shop. Same thing as a human. Gotta take them to the body shop. So that's just basically what we're doing. We're looking at the function of how well the heart is pumping its blood out, like the engine, how well it's functioning. Okay, so I'm going to come back to this, but right now I want to talk about another important idea first. Okay, so let's talk about another guy first. This guy is named Robert Boyle. He was born a little bit earlier than Dr. Wiggers in 1627. Anyways, important stuff. He came up with a law relating pressure and volume. He said pressure equals 1 over volume. That's its relation. So what does that mean? Does that mean pressure and volume are directly or indirectly related? Well, let's find out. So let's say we make a box right here. Okay. And then we put inside it, a couple people. Alright, I'm going to use red. Obviously you probably know why, because later it's going to be representing the blood. So we'll put about 6 people in here. Just their heads. They're all happy. There's their eyes, they're hanging out, having a good time inside this box. Okay. And now we're going to make another box. Well, what's going to happen to this box? I like to call this my haunted house analogy. So if you're in a haunted house, you're inside this box, and then the walls are going to start to get pushed in on you, and they're going to come in. So it's going to be a much smaller space in there. Still the same height, just smaller width. So now these people are inside. There we go, the same 6 people, and they don't have as much room to move in. So they're upset. There they go, got little upset faces. Okay, so what just happened? Where do we have greater volume? Over here in box 1 or in box 2? Well, in box 1 we have greater volume. In box 2 we have a lower volume. But what about the pressure? Who's feeling more pressure? When they were in box 2 or when they were in box 1? So when you're inside a big box, you have a lot of room. There's not much pressure, you can move around. But when the walls come in, you're stuck. You can't push out, so there's a lot of pressure. So small volume, high pressure. Large volume, low pressure. Okay, so we have a large volume here, so it means we have a low pressure. We have a low volume here, so that means we have a high pressure because everybody is, pushing against the wall. Here, they have so much more free room to move around. So pressure and volume are inversely related. One goes up, the other goes down. If this goes down, then this one goes up. And it's a cycle, so it alternates. So if this is a ventricular chamber, it is going to contract, and we have the pressure going up. And then we're going to come back and start over when the ventricular chamber relaxes. And there's a few more steps we're going to insert in between there, but that's what we're about to get to next. But that's just definitely important because we'll see the pressure and the volume and all those relations that happen when we come back to this at the end. So now let's start something new. I made a series of 7 steps of what's going to happen inside the ventricle, and we're going to stick to the analogy of the haunted house. So with step 1, we are going to make a box. And please excuse my horrible drawing. And on this box, we're going to have to make a door to enter and a door to exit. This is the indoor. This is the outdoor. Again, this is step 1. So in step 1, alright, this is a haunted house. Remember what happens in the haunted house? Well, go back up here. The walls start to come in. That's why it's a haunted house. The walls start to come in. Excuse me. The walls start to come in and scare the people and increase the pressure inside. Alright, so we're starting with our haunted house. The people are going to start to come in, which is going to mimic the blood flow coming in. So they're moving in there. Okay? And they're all happy. They have no idea what's about to happen to them yet. They're just sitting inside. So they're making their way inside. So naturally, the door to enter has to be open so they can get in. But why is the door to exit closed? Well, if it was open, then they would just leave right outside that door. So they can't do that because the door is closed. So now, step 2. We'll draw our box again. The door is still open in this case. And the exit door is still closed. We'll draw our people. I'm going to stop drawing the faces right now. I'm just going to draw the circles. So they're all inside. Doesn't matter. They can be inside anywhere. And there's still those 2 stragglers left in there. So what's going to happen? Well, these guys have to be forced in. They're going to be kicked in now. So these guys just got kicked in. Just for fun, I'll draw some guy that just gave them the boot. Just kicked them in there. Alright, they just got a forceful kick inside. Here, in step 1, they walked in by themselves. In step 2, the guy's like, alright, the show's going to begin. Here's the haunted house. Get in there, whatever few of you that are left. Alright, step 3. So now the show is about to start. We got our box. We got our guys that are just chilling out inside of the box. The exit door is still closed. And now the enter door just shuts right behind. So the door closes back. So right now these guys are happy. They're just hanging out in there. They have no idea what is about to happen to them. Step 4. The walls are about to start squeezing in. Here comes the real fun. So now the box has gotten much smaller. Here they are, the same 6 guys inside. This time they're not as happy. Alright? Okay, so we're building a lot of pressure. The walls are squeezing in. So what's eventually going to happen? So let's take this water bottle I got here. Let's say, we filled it up a little bit. Let's pretend there's 2 tops. There's this top right here, and there's another top right here underneath my finger. So if I would squeeze on this bottle really hard, one of the tops is going to have to pop off. This one is going to be the top one, our enter door. So that one's on tight. It's being held down. The other door, if I squeeze, boom, that's going to pop off. The water is going to spray out. I didn't do this for this example because I don't feel like shooting all the water all over my computer, but you guys get the point. There's so much pressure in here that that's going to pop off and the water is going to go out. So you just saw step 5. The box is compressed. Erase this. And the door pops open. A bunch of the guys get ejected out of that haunted house. Some remain inside. They're all excited. They just flying out. They're just ejecting out of that box. Remember, it's that force of that ventricle or this haunted house wall that's pushing in on them that's forcing them out. And keep in mind that top door is closed. Well, what would happen if that was open? Well, they would go the other way. Something you'll learn about, which would be regurgitation, going backwards. In the analogy of the haunted house, we don't want them to go back out the way they came. We want them to leave out the exit. Step 6. The box or the haunted house is still squeezed. What's the same is that the enter door is still closed and the exit door now shuts behind. The door just swings back. And we are still remained with about 2 people or so left. Our last step, step 7. Now look back at step 6. The door's closed. There's still some people in there. The guys that got kicked out. So now it's time to open this box back up and let a new round of people in. So the walls are going to start to expand. They're going to start to come out. So they are starting to expand. It's going back to its original shape. Keep in mind the doors are still closed here. And the walls have expanded. We still have the same 2 guys that are in there because nobody could go in or out. And then it's time to repeat the story back at step 1 and open the door and let a new round of people go in. So it is a cycle right here. Okay, let's scroll down a little bit. Let me show you something I came up with. Let's draw a nice, wonderful Valentine's Day heart. There we go. It's one lovely heart. And let's partition it into the 4 quadrants that I'm pretty sure you already know. We have right atrium, right ventricle, left atrium, and that leaves us with left ventricle. So what did I do with this? Well, alright, which one of these chambers is the thickest? It's going to be the left ventricle. Why left ventricle? Well, it's going to pump to a further distance. Is that to the lungs or to the body? It's going to be to the body. That's called your systemic circuit. So I took this left ventricle, and what's the enter door that allows blood from left atrium, left ventricle? Right here. That's going to be your left AV valve, also your mitral valve, also known as your bicuspid valve. What's the exit? Well, it's going to be this big structure that goes up and around. That's called what? Yes, that's called the aorta, and that's where the blood is going to flow out of. And then there's going to be a valve on that as well too. So you can see our analogies here. Just like we have an indoor and an outdoor, we have the indoor right here. That's going to be our AV valve. And then we have our outdoor right there, which is going to be our semilunar valve, left semilunar or aortic valve. So that's what these represent. Right here, the end, that represents the AV, and the out right there represents the semilunar, all the way around through the rest of the diagrams. So what I want to do is just isolate this left ventricle with the aorta. So if we draw a piece here, over here, down like this, the aorta coming up and around, we'll get this. We can have our valves. It could be open here, open here, open here, and open here. So this area here, that's going to be our left ventricle that you see over here being outlined. So let's continue to tie in the heart with this diagram I came up with. So I made this little chart. I'll give you a link. You can download it when you want, and the answers with it too. I put the 7 steps outlined like this, And again, what ventricle are we looking at? We're looking at the left ventricle. It's the strongest, so we're going to evaluate its function. Okay, so we start off here, passive filling, or passive ventricular filling. Well, it's got to fill up. Again, this is a cycle, so you can start anywhere, but it's got to fill up. So the blood is going to start to come in here, and it's going to start to fill up the ventricle. Since it's filling up, this valve has to be open so the blood can get in. But what would happen if this valve, the SL valve, was opened? Well, the blood would go in and it would rush right out of the aorta. So this valve here has to be closed. So over here we have our AV valve, our bicuspid or mitral, since it's the left side, and over here our SL valve, which would be the aortic valve. So the AV valve is open, that's why we can get this blood to rush in through here, but the SL valve is closed. So this was just passive, it just happened without force. But remember, when we go back to our haunted house analogy, okay, step one, passively, people just walked into the haunted house, but what happened next? We need to still get some people, so they were booted into the haunted house. So what does that booting represent? Well, this valve still has to be open. The AV valve still has to be open, but this one is closed, so the blood doesn't go out. So we get to fill this up a little bit more here. So the SL valve has to be closed. All right, so over here, this actually, if you want the values, fills up about 2/3 of the way passively, and over here 1/3. We also call this atrial, I can't really write here, atrial systole. So it kicks in, that means systole, it's getting contracted. How can you remember systole versus diastole? Well, systole starts with the S, think of squeeze. Alright, it's getting squeezed into there. Diastole, think of dilate, opens up. So again, the AV valve has to be open for the blood flow to come in, but the semilunar has to be closed. Now let's move to the next thing. Just think back to the haunted house. Everybody came in. The passive people came in. Those people got booted. Everybody's inside now. What do we have to do? Well, do we want to open the exit door up? No, not yet, because we still haven't done the whole haunted house situation. If we go back to the haunted house, you take a look. All right, everybody comes in. Boom. All right, now we slam that door shut behind us, and that makes a big noise. That big noise slamming is the closure there of the AV valve as it slams shut. Just think about it. Go slam a door. When you hear a door slam, it's going to be pretty loud if you slam it hard enough, and that's the heart sound. So that is going to be the S1 heart sound. So the AV valve just closed, and the SL valve was already closed like before, and we still have that ventricular chamber all filled up. So think about the haunted house before I show it to you. Just think about it. Everybody's inside. All the doors are closed. What's the next thing you're going to do inside of that haunted house? So we go back, take a look. You see everybody's inside. Boom. That's S1. That's switch valve. That's going to be the AV valve. And then here come the walls. They're squeezing in, and there's a sudden increase of pressure. Okay, so the walls are going to start to be squeezing. They're going to come in like that. You're going to have that decreased volume inside there. Both doors are still closed. We still have the blood that is inside of there, but it doesn't have much room to move around. Again, the AV valve is closed. The SL valve is closed. Now look at this term here, isovolumetric. What does iso mean? Isotonic, isometric. Iso, if it's between hyper and hypo, iso means the same. Same what? Same volume. If you look in there, the volume or the number of people is not changing. Go back to our haunted house example. See, we had 6 people, and we still have 6 people. Even though we changed like the size of the room, it's still the same volume, still the same number of people. And what happened to that pressure? is that pressure shot up. So in ISO, volumetric contraction, the pressure is going to start to shoot up. Now I'll show you quickly the Wiggers diagram, and I'm going to come back to it more. If we take a look at it here, ISO volumetric contraction, look at this blue line, how great that pressure increases right there. ISO volumetric contraction. Okay, so going back down here, what's the next thing that's going to happen? Alright, we're squeezing, the pressure is building up, it's so high, there's great pressure. Well, what's going to open up, the enter or the exit door? Well, if the enter door opens up, we're going to get some regurgitation, we're going to get a murmur, a heart sound. We don't want that. So what's going to happen here is there's going to be so much force that it's going to force it out of this big structure, and that's the aorta. So again, it's squeezed, there's a lot of pressure in there. This is going to be closed, so our AV is closed. But what just opened up? Our semilunar just opened up. Just draw it like this so it could get out. So a lot of that volume is starting to rush out. Alright, the people are leaving the haunted house. Some people are going to leave, and then after the people leave, what's going to happen behind them? Yes, that door is going to shut. We don't want to open up the enter door yet because we got to close the exit so anybody who's coming in doesn't go out right away. The ventricular wall is still pretty thick right here. It's still contracted. A lot of the blood has just rushed out. There's still a little bit left in here. So the condition of this valve, closed and closed. Alright, so remember the walls are still caved in, they're still pressed in like this over here, they're still pressed in. We don't want people to come in while the wall's already closed in. You know, they want to be surprised when they come in. We need it nice and open. So what's going to happen are the walls are going to start to expand and start to open up. So the doors are going to remain closed here, closed, and closed. And now we have a little bit of volume left in here. And as you notice, ISO, volumetric, but this time relaxation because we are relaxing. Versus over here, we are contracting. So let's go up just to the Wiggers diagram really quickly right now and look. ISO volumetric contraction, look at that steep incline right there. ISO volumetric relaxation, look at that steep decline in pressure. Let's go back down here. Another thing I wanted to mention is that the S2 sound right here, S2, what did that come from? Well, if you look, the SL valve was opened and then it shut, closed. So the closing right there of the SL valve, that's your S2 heart sound. If you go back up here to the haunted house analogy, all right, everybody got booted out, and boom, the door shut, closed. That's your S2 sound. That's your SL valves. And then we go back down here, and you can see the cycle is going to repeat itself. Everybody got booted out, the walls opened up, and now we need a new round of people, a new round of blood to come in here. Whether you say it's 2/3 or 75%, it's all the same thing. And over here, 1/3. The big important part is, you know, the majority is coming from passive filling, and then the minority, 1/3 about it, is coming from active filling. That's where the atria sits right up here. It squeezes, goes through atrial squeeze, atrial systole, atrial contraction, all the same thing to force the blood into the ventricular chamber. So now let's relate this diagram to the graph, the part you want to get down to. So let's look at number one, all right, passive filling versus active filling. So we're going to fill up 2/3 first passively and then 1/3 next actively. So we'll go up, and if you take a look, let's say we start up right here. Okay, this over here is volume, over here is pressure. Whenever you see a graph, look at the x-axis. It's not labeled here, but I'll tell you it is time going this way in milliseconds. And over here we got volume, over here we got pressure, over here we got the AKG and heart sounds. So let's look at the volume first. Okay, so the first part right here, that's filling up 2/3. How did everybody get into the haunted house? 2/3. They got in passively. And then there's another 1/3 right there. They got actively. What happened? Well, the atria was kicking. If you look at the P wave represents atrial depolarization, or it's telling the atria to contract, and then it's going to fill up the ventricle. So now we kind of know where to start. I mean, it's a cycle, so you can start anywhere, but let's take that point over here. Right? So we'll go over here. Let's start right here. It says mitral valve closes. The mitral valve is the AV valve. AV valve was the indoor. So everybody's in, right? Let's go look at that picture. Now everybody is inside. Everybody's inside. Boom. We close. That's the AV. That's the mitral valve. So we get mitral valve closes. When everybody was inside, think about it. Everybody got inside. What happened next? Doors are all closed. Boom. We got our S1 sound. And then all of a sudden, the ventricle walls are going to start to come in. And what happens to the pressure? It dramatically increases. Is anybody going out? No. So we're keeping the same volume. This is ISIL. So let's go back up here. Okay. So there, the interdoor closes. We start to squeeze the ventricle. That's the QRS telling you ventricular depolarization. That signal is sent. As soon as it's sent, boom, look at that dramatic increase in pressure. Until finally what happens? Well, the aortic valve opens. Let's go. So the aortic valve is going to open up. Everybody's going to eject out, ventricular ejection, because you can imagine it like somebody standing here at this door. They're holding the door shut, and once the pressure becomes so big, it's stronger than this guy out here, stronger than the valve, and boom, it's going to eject out. So over here, here's the guy. He's the one that's holding on to the door right here. The pressure gets stronger, boom, and the aortic valve opens up, and we have ventricular ejection going out the aorta. And if you notice, 120/80, that's our systolic over our diastolic pressure going out. Everybody goes out. What are we going to do? Well, we are going to close the door that everybody went out on. Go back down here. All right, so everybody goes out. Boom, that's our S2 noise. That's what we're going to close right there. And if we look over here, down here, S1. Alright, what happened? The interdoor closed, everybody went in, closed. Here, everybody's going out, the exit door closes behind them. Boom, that's the S2 noise right there. And then going back. Alright, we already kicked everybody out, the doors are all closed. It's time to open up the walls. And you can see that increase of volume there. So we're going to have a dramatic decrease in pressure. So if we go look over here, the pressure starts to decrease dramatically, and then we're going to start the whole cycle again. We're going to fill up the ventricles passively, not too much change in pressure there, actively a little bit, and then start it over again. If you notice mitral on the left, on the other side mitral again, one closes, one opens. Same thing, aortic up here, opens and closes. So just think about them as enter and exit doors, and you should be able to do it right and draw it out a couple times. Right? And this is the volume, 2/3, 1/3, 2/3 passively, 1/3 actively. And hopefully this helps you out. Okay, so review it a little bit, but if you're ready, let's do a quick few questions right here. Okay, so question number 1. During isovolumetric, so iso meaning same, contraction, systole, what are the states of the valves? Isovolumetric contraction, so you could draw out your ventricle, you could draw the aorta coming out, You have your valve. Here's the other valve. Okay, ISO volumetric. So it's saying contraction. So let's say the walls are going in a little bit, walls going in, it's squeezing in here. Alright, but is anybody going out or coming in or anything? No, it's ISO. The number of people are going to stay the same inside, so the state of the valves is going to have to be what? Closed and closed, so that's going to be choice B. Okay, you can pause it and think about the next one, but I'll continue. During ISO volumetric, sorry, I wrote contraction. I meant to write here relaxation. During ISO volumetric relaxation, not systole, but what? Diastole. I just copied and pasted. What are the states of the valves? So relaxation, so the ventricle is going to relax, is going to open up. Are the valves going to be open or closed? Well, ISO, alright, ISO, so it doesn't mean anything's changing, so both valves are going to be closed, so it's still the same answer choice, choice B. Well, but what's the difference here? Which one has a higher pressure? Well, the walls are coming in here, they're pushing in dramatically. Remember the box, when we don't have much room, pressure is going to increase. Over here, it's going to decrease. So if we go back up top, and we take a look here, you'll see isovolumetric contraction is this little area in here. Look how much it goes up. And isovolumetric relaxation just in here, it goes down dramatically in such a short time. So let's go do the last question here using the chart. Which point on the graph below does the SL valve close? So you know what? Here's another thing, by the way, if you want help remembering what valves to enter, which ones the leaving. So the AV, you're going to approach, go in. The SL, yeah, semi-lunar, but I call it the see ya later valve. SL, see ya later. So that's going to be the exit one. So at which point on the graph below does the see ya later valve close? Now don't write see ya later on our test, but just so you can remember, see ya later valve, semi-lunar valve is going to close. So that's going to be, when is the exit door going to shut? Well, everybody has to leave first. After everybody leaves, we'll shut it. So you walk through your steps, right? Compare your volume, go back and forth. You'll get better at this. So everybody, this is volume. So we are at our maximum volume here. Everybody's in. So then what's going to happen is we got that message to contract the ventricle, the QRS. Boom, dramatic increase because everybody's getting squeezed in. Then we're going to eject everybody out. Once everybody's ejected, once they're out, boom, we're going to close that door behind them. So at which point does the SL valve close? That's going to be point C right there. So the SL valve closing is the beginning of isovolumetric relaxation. And then what's going to open up here? Well, it's what closed over here. The enter door has to open up again so we can get a new round of people or a new round of blood. That's going to be your AV or your mitral or your bicuspid. Alright, good luck with all this. If you have any questions, you can email me, JROUFAIL@gmail.com, or you can find me on Facebook. My first name is John and last name is Rufael. Good luck. I wish you guys the best.